Hello to everyone.
Hello, Marco.
Good to see you. Thanks a lot for your time. Thanks a lot for your availability of being here today. And so just a couple of technical aspects. I just turn off my mic. Okay, just a couple of technical points before we start. I will send to you a document where that you have to sign it to give to the president of the jury the right of signing the final decision we will take on your behalf, since you cannot be here in person. Which brings us to the second point, which is we need to have a president of the jury today, which cannot be me. So I don't know. I was thinking perhaps Jean-François, would you, since you are French, so you know the system better than also Barbara could be, because she is part of the. But
if you wish, just since I'm
exactly.
from Pisa, yeah,
probably is not the best option. So Jean-François, would you agree to be the maître de cérémonie?
Are you sure I can be with being the referee and also the president? It's not a problem.
Yes, you can.
I think you can be. Yeah.
Okay, let's do it like that.
Okay, thank you very much. Okay, so I think we can start. So perhaps Jean-François, I don't know if you want to. Usually the president introduces the jury, and then we can leave the mic to Santiago. You can start with.
I will have some trouble to introduce the jury. I need to find the manuscript first.
Okay.
Wait a second.
We don't have a speaker.
Exactly. Okay.
Does it work?
Okay. Do we begin?
Yeah, let's start.
So we are here all together for the defense of Santiago Smith Silva Rincon, and the jury is made up of James Coles from the Dementia Research Center, Institute of Neurology, UCL, Jean-François Mangin, myself from University Paris-Saclay Neurospin, Marco Lorenzi, who is a supervisor from INRIA Sophia Antipolis, Barbara Bardoni from INSERM Sophia Antipolis, co-supervisor, Jonas Ricciardi from Lausanne University Hospital and University of Lausanne, and André Altman from the Center for Medical Image Computing, Department of Medical Physics and Biomedical Engineering, UCL2. So, Santiago, if you're ready, it's up to you. You have about 35 minutes to present your work.
There is an icon. There is an icon.
No.
I think it's fine. Cool. All right. Thank you very much. So let me share my screen for starters. Cool. You should be seeing my screen by now.
Yeah, it's fine.
Cool. Yep. Perfect. Thank you very much. So first of all, good afternoon, respected members of the examination committee, esteemed colleagues who are present here, and distinguished guests. I'm delighted to be here today to present my thesis on federated learning of biomedical data in multicentric imaging studies. My name is Santiago Silva, as some of you may know, and I would like to express first of all my gratitude for this opportunity to present and discuss my research findings with you all. So first, I would like to walk you through some context on the multicentric studies, and particularly in neuroimaging. So data in neuroimaging keeps being produced at high rates, opening the door to new insights in neuroscience research. A great example of this is the Image and Data Archive, a multicentric image initiative with millions of downloads since its creation in 2016, and with more than 150,000 users, where most of them are researchers. However, in a more typical scenario, multicentric data access is hindered by constraints, such as ethical committee approval and transferring the data to a centralized location, like a research facility. This has become harder with the recent regulations, such as the GDPR, which need also to be respected when conducting multicentric studies. Commonly, in order to circumvent these restrictions, two main methods of analysis are followed. First, we can go for meta-analysis, which do not share individual patients' information, but instead they share statistics. For instance, mean effects of a treatment, p-values, or odds ratios. Although rather secure, they may lack of a statistical power, and global pre-processing cannot take place, like a standardization or harmonization, given that the data is decentralized. Mega-analysis, on the other hand, allow for sharing either raw data or derivatives from it, and it gives place to a global pre-processing step and also have higher statistical power. However, it does compromise individual patients' data. Addressing these challenges of data governance, Google introduced federated learning in 2016 as a solution. This approach enables the training of models on multicentric data without requiring data centralization. In a particular setup, in an industrial setup, a central server would coordinate the communication with the participating institutions. In our context would be hospitals, which instead of sharing data, these institutions would contribute by partially training a model on their data and sharing back only its parameters. These parameters are then combined in a process known as aggregation. This aggregation process normally considers for size effects, and one of the most widely used methods for aggregation is federated averaging, which is the one we used along this work. And federated averaging, as shown in step 3, aggregates the local models using a weighted average. This aggregation is normally done in an iterative fashion until convergence is achieved. There are multiple challenges associated to federated learning and multicentric studies. Amongst the ones we try to tackle, there are, first, handling heterogeneous data coming from multiple sources or institutions. This means accounting for biases due to systematic errors, size effects, or any discrepancies on the data covariates. This means how ID or non-ID the data is distributed. Secondly, defining a common framework for federated learning that is transparent, that encourages reproducibility, and that is compliant with current regulations. It's imperative to conduct real multicentric studies following a federated paradigm. And finally, we try to tackle resource utilization, which can be very often a bottleneck in federated learning, as not every hospital can count on specialized hardware to train the models within the scope of federated learning. Just to set an example, neural networks. I would like to dedicate some time in particular to the first problem, heterogeneity, as it is the matter of 2 chapters in this thesis. And in particular, I would like to focus on systematic errors, which is one of the main sources of bias in neuroimaging studies. Bias due to systematic errors can be present at different stages in neuroimaging data production. On the scanner side, for instance, where different brands have their own protocol acquisition, or also going to calibration protocols that may vary across institutions, altering thus the final result in the image production. Additionally, the use of the software versions or pipelines across hospitals during the feature extraction process can additionally introduce these errors. As all this production is chained, we decided to focus on the final stage, considering that changing the previous 2 would involve creating either industrial or acquisition standards, and we would rather focus on the exploitation of the already existing data. Systematic errors can either be corrected or incorporated within the models. Correction is a widely accepted approach, and typically it is executed using methods like a surrogate variable analysis, or more recently, the combat model. Other techniques may include like mixed effect models or conditional deep models, as it is the case of the conditional variational autoencoder. Combat in particular is the most widely used method of harmonization in neuroimaging. This method was initially proposed by Johnson and colleagues in 2006 and lately extended for neuroimaging by Fortin and colleagues in 2017. Combat aims to remove biases due to systematic errors while preserving covariate effects. This means, for instance, removing the effect of a scanner brand without removing any differences with respect to sex, age, or controls to case differences. This is achieved by Fortin and colleagues who suppose a linear model on the effect of the covariates on the measured phenotypes. This linear assumption can be weak, as recently shown by Bethlehem and colleagues in 2022, as age has a clear nonlinear effect on the brain atrophy. Combat GAM, on the other hand, which is a method proposed by Pomponio in 2017, relies on generalized additive models, which try to approximate such nonlinearities using smoothing functions like splines. However, the nonlinear effects need to be defined a priori by the researcher, otherwise they will be just considered as linear. These methods only exist in a centralized setup. An initial decentralization approach was proposed recently in 2022 by Chen and colleagues by relying on the properties of covariance distribution matrices to be able to be computed in a decentralized fashion. And this method was called D-combat and was able also to recover the parameters of the neurocombat model proposed by Fortin in a decentralized setup, although this formulation is still linear. So with this, we aim to contribute to the state of the art with this thesis as follows. First, we try to address data heterogeneity issues in decentralized setups by proposing a generalized formulation of the combat model that would account for nonlinear covariate effect preservation. And also we explore the potential of conditional generative models, all of this within a framework of federated learning. Secondly, we try to relieve the optimization from the hospitals or institutions without the specialized hardware by centralizing the optimization and at the same time keeping the data decentralized. We aim to do this by relying on a federated Bayesian optimization approach. And finally, in order to conduct real federated research studies, we propose a common federated medical framework to do so. So having provided an overview, I will start discussing our first part related to chapter 2 in the thesis, which we decided to entitle A Generalized Framework for Data Harmonization in Federated Setups. This work has been submitted to Human Brain Mapping this year and is currently under review. So first, to illustrate the objective of harmonization, let us consider the following scenario. Imagine we have collected a particular phenotype from multiple institutions. However, due to variations in data collections, protocols, or equipment, a systematic error may arise, introducing differences then in the data originating from these different sources. With this in mind, the goal of harmonization is then to identify and learn the most representative distribution that allows for fair comparison across the data without disregarding the characteristic shape of the actual distribution that is resulting from the conditioning variables of interest, like age, of sex, or a diagnosis, as I mentioned before. So to account for this, our proposal is still inspired by the combat model of Johnson and colleagues. And for this, we need to think of a phenotype that G that is originated at a site I and belongs to a subject J. This phenotype can be then approximated by two big components. First, let's consider some fixed effects that are denoted by a fixed intercept here as alpha G, and a second mean effect that is defined by this covariate effect approximating function. This covariate effect approximating function is depending on covariance and is parameterized by theta G. Also, let's consider some random effects. First, a random intercept that will try to shift the distribution of the phenotype. And secondly, a variance scaling factor that will alter the shape, the spreadness, let's say, of the distribution. The phenotype variability at the end is captured by the noise model epsilon defined within this model. And our main contribution with respect to the state of the art is proposing phi as a general approximator that could be any arbitrary function that can be parameterized by theta G. Phi would generalize, for instance, the combat case where phi would become just a linear transformation, or the basis decomposition of combat GAM. So this is a more general representation, and combat GAM become two particular cases of it. However, for the case of federated learning, we decided to propose a more complex and suitable model for federated learning. We decided to go for the multi-layer perceptron as it is considered to be an universal function approximator. Additionally, the multi-layer perceptron would allow us to have a more flexible modeling as it can be tuned. It is multivariate as normally it is fully connected, so it can account for covariate interactions other than linear, and it is extensible to a federated learning setup due to its gradient descent optimizable nature. So in order to train such a model in a federated setup, it is necessary first to estimate the fixed effects and have a first estimation on the random intercept as proposed by Johnson. This is achieved using federated averaging iteratively and controlling for overfitting by using a cross-validation scheme. With this first estimation, the phenotype variance, which is also aggregated at the end is considered a pooled variance, can be calculated and then a standardization step, which is what you see on the bottom part, as Z is computed. So the distribution of Z becomes a normal that is parameterized by only the random effects, gamma and delta. With this transformed data, we can then just proceed as Johnson proposed with the estimation of the random effects. And this is done by using empirical bias. As shown also by Chen and colleagues, the creators of the distributed combat, the estimation of these parameters is only indexed by the phenotype G and by the site I, making this estimation local and not having any need for communication with the other institutions. So once these parameters are estimated, they can be used jointly with the learned covariate approximating function, as you see in step 3, to harmonize the transformed data, meaning subtracting the shift, rescaling the data using delta, and finally adding back the mean effects described by alpha G and the covariate effects described by the learned function phi. So for the sake of comparison, we consider it pertinent also to propose a distributed version of combat GAM, and we decided to call it the combat GAM. The nonlinear effects are interpolated in this case similarly to the method of Pomponio and colleagues via the composition of bases, here denoted as B, that are basically just smoothing functions such as splines that try to interpolate the nonlinear effects. At the end, this problem becomes still a generalized linear model, which simplifies the estimation of the parameters, here denoted by theta. And similarly achieved by Chen and colleagues, the estimation can be done by just distributing the computation of the covariance and the cross-covariance matrices. Additionally to this, as recently some authors have been discussing and exploring the risks of data leakage through full covariance matrices, we proposed and we extended this work based on previous work we did in 2019 to share, instead of the full covariance matrix, a partial eigendecomposition of each which would result in approximate results that are fairly comparable, doing before all of this before aggregation. So we decided to benchmark our model first on synthetic data. We decided to focus particularly on non-ID data scenarios, which are the one below on the right. Given that they are known to be the most challenging and the most similar to real-life scenarios. For the generative graph model, we took inspiration from Reynolds and colleagues in 2022, and it's the chart that you can barely, I guess, appreciate from the left, on the bottom left part. So on the top left here, you can see what we decided to call the unbiased target function, which is hidden from the harmonization method. Retrieving this function is the ultimate goal. In this case, we simulated arbitrary trajectories of a phenotype and categorized for two populations, in this case, simulating male and female populations. Color allows to identify from which institution the simulated subject belongs to. We then bias the data as shown on the top right and proceed to harmonize this new data set. So below you can see already two methods, the neurocombat method, which is the linear centralized one, and the proposed federated multi-layer perceptron combat. And you can clearly see a clear improvement when it comes to the estimation of the trajectories. And this case is particularly obvious because the function is nonlinear. In contrast with nonlinear methods such as combat GAM, a more thorough comparison was needed. So we showed on the right, on the two right plots, the blunt Allman plots, which allows us to visualize the remaining age and side effects that haven't been captured by the model. Also, the root mean square error, and as you can see, the multi-layer perceptron does slightly a better job. In terms of mean absolute error, it seems to be similar across methods, which is the first column on the left. However, the root mean square error is more sensitive and penalizes larger errors, so we can identify better the differences, which is the column on the extreme right. In terms of error variability, which means how precise the method is at estimating the unbiased function, we can see that our approach methods perform more accurately when it comes to the estimation of this function. For our test on real data, we relied on 9 cohorts for a total of more than 7,000 subjects diagnosed as cognitively normal with Parkinson's, Alzheimer's, and within the autism spectrum disorder. As you may be able to appreciate on the extreme right plot, the data distribution is quite non-ID, similarly to the synthetic data. Some cohorts don't even overlap in terms of age, as it is the case of the top and the bottom one, which correspond to a BID and day 4. So to confirm the presence of nonlinear covariate effects in our cohorts, we decided to perform a model comparison in terms of archaic information criterion. 2 models were compared, a linear regression model and also a GAM as proposed by Pomponio and colleagues. On the left, you can see we illustrated the areas where the nonlinear model was able to better fit the nonlinear effects of the covariates. And this is represented here by the most highlighted zones. On the right, we illustrated the 3 most nonlinear regions that after correction using linear combat, still show that trend on the residuals, which is the right column of the plot on the right, indicating the need of a more complex model. Then we decided to estimate the aging trajectories for typical and atypical cohorts, groups. And we estimated this for centralized and decentralized methods. Here we illustrate the same top 3 using non-harmonized and only the distributed methods. Otherwise, it would have been too much information. And here we focus on distributed combat, which is the existing state of the art, and our proposed methods, the combat GAM and federated combat using a linear approximating function, and federated combat using a multi-layer perceptron, respectively. So taking a closer look at the right hippocampal growth trajectory, distributed combat seems to exacerbate atypical atrophy with respect to combat GAM, which seems even to suggest hippocampal enlargement after 50 years old. And federated combat seems to better understand the plateau between 23 and 65 years, and it does have a less pronounced rate of atrophy for atypical groups. The atypical group being defined mostly by Alzheimer's and Parkinson's disease patients. All these insights, of course, require clinical validation. So based on the insights gained from this work, we can draw the following conclusions. First, we propose a harmonization method that was able to preserve nonlinear effects of the covariates on the phenotypes. Secondly, this method is federated, which differentiates it already from the state of the art, and also is multivariate in the sense that it does account for relationships between covariates other than linear, as it is the case of combat or combat GAM, where you may need to define them a priori. Some limitations are identified as well, such as Fed combat require more rounds of communications with respect to D-combat and D-combat GAM, which are one shot, and requiring maybe sometimes more computational resources as the number of parameters increases. But and additionally, and not less important, having exploring only tabular data, and this opens, of course, some perspectives, like trying to extend this method to the voxel-wise level, trying, of course, as I was mentioning, clinical validation of these results, and also evaluating if just a shift and scaling parameter are enough as the random effect in this model. So in the look for more generalized models, we decided to investigate the potential of conditional deep models, as well as their potential applications in harmonization. So we have decided to take a particular look to conditional variation as autoencoders. This work corresponds to the chapter 3 in the thesis. So this work was basically conceived after realizing that the combat model accounts for a random intercept, a variance scaling factor, but the covariate function was not considered to have a random effect. We started first by defining a sort of random mixed effect modeling that was generative, that also considered a random slope here denoted as omega ig. However, we discovered later, but we were aware later, that in 2016, Sean and colleagues proposed an even more generalized method, the conditional variational autoencoder, whose aim is literally to approximate the distribution of the whole data, while disentangling the observed unobserved condition, such as the side effect in our case. We trained then this conditional model to approximate the joint distribution of phenotypes and covariates all together, and here is denoted by X. And we condition this process by using the batch information, meaning the site or in the scanner in some cases, and this is denoted by Y. As this model is gradient descent based, we use federated averaging as the federated optimization approach. And once the model was trained, instead of we perform multiple forward passes by sampling from the categorical distribution of Y instead of passing the actual batch information. With P, the parameter P being the probability of each site or scanner or batch effect to be sampled. So at the end, we would end up with a reconstructed measure whose batch effects would had been averaged out. In other words, harmonized. So additionally, to reduce the risk of overfitting, we decided to consider a Bayesian approach on the parameters that would penalize them in the evolution of the model. And this was done by using an extra Kullback-Leiber divergence term in the evidence lower bound that was able to regularize, as I mentioned, the evolution of the model parameters. We were able to regularize this, as I mentioned, and although this also had a sacrifice, which was a longer time of convergence, as the number of parameters would increase significantly. So once again, we can see the blunt Allman plots for a synthetic data set with side effects introduced. After harmonizing with the conditional variational autoencoder, considering each site as the batch effect, we can observe that there is no evidence of side effects left after the harmonization. And more particularly, when performing PCA on the feature space and using ANCOVA to see, evaluate the presence of these side effects, we can see on the top and the bottom figures that there is no presence which correspond to the unbiased and the harmonized data. The one in the middle corresponds to the biased data. So additionally, we could get some results compared to the federated combat method, which was the chart we saw before, and the reconstruction task. And we can see here that although it seems comparable with the Fed combat, the multi-layer perceptron, in terms of the blunt Allman plots and the root mean square error, it has a larger error estimation. So it has particularly more variability when it comes to the estimation. And this is very known of conditional variational autoencoders, that they can be sometimes a bit more noisy. We additionally also created trajectories, the same task as shown before, but adding the conditional variational autoencoder in this case. And more closely, as a result, we can see that the combat still suggests a faster growth for atypical trajectories on the right hippocampal area, while we can see that the conditional variational autoencoder seems once again to understand the plateau a bit better. And also, it seems to suggest that early onset decline on atypical populations described here as Alzheimer's and Parkinson's, as I mentioned before. And in particular, there is a lower volume for the ASD group, this meaning the group diagnosed with autism spectrum disorder, which is still a subject of discussion in the literature. In young population, because the young population in particular here belongs to an autism study, here established as well, mostly by the ABITE cohorts, the conditional value still preserves the amygdala enlargement in adolescents and adult groups, as also reported in the literature. So after this exploration, we could conclude that this method may open the door to more complex tasks, as like voxel-wise image harmonization. And this in particular because we can introduce convolutional layers here with respect to the multi-layer perceptron. So thanks to the nature of this model, it can also be trained in an unsupervised manner, meaning we can harmonize data from sites that we may have not seen before, as was the case of Garcia and colleagues who tried to do this with the linear version in neuroharmony. And also an extended comprehensive benchmark and comparison needs to be defined to better understand how conditional models perform with respect to the other methods. And as well, of course, some limitations we identified during this work. The first one being requiring even more communications, given that we have additional parameters. And also, we also identified some perspectives as recently realized, having the opportunity maybe to propose, to extend this work, to more defined tasks, such as the OpenVHB challenge, which is a brain age prediction challenge that needs or requires site removal. So this is a probably interesting perspective. So during this work, we also decided to turn out our attention towards improving the optimization in federated learning, particularly when resources may not be available, as in the case of some hospitals. In this section corresponding to chapter 4, we decided to explore the potential of Bayesian optimization for federated aggregation. So Bayesian optimization is a gradientless technique that allows to optimize any parameterizable model, also known as black box models. Sorry. It is particularly useful when evaluating the response. For instance, the loss function is expensive computationally. Bayesian optimization tries to approach the response function, or the loss function in our case, also known as the loss surface, as a multivariate Gaussian process. The optimal solution is then the result of optimizing such a process. But this applied to a federated setup becomes slightly different. So instead of relying on each institution to have to optimize a model locally, we would only send a set of parameters and ask them to evaluate their loss without doing any optimization. Then the proposed parameters would be collected and used in the central server to train and try to reconstruct this loss surface using a Gaussian process. Followed by optimizing this utility function that you see on the top, on the bottom, which is called the expectation improvement, but there are some others that try to find a balance between exploring unknown areas in the search space and proposing the actual minima of the Gaussian process. And with this optimization, we would find what is the optimal next candidates that will be shared or sent back to the institutions to be evaluated, and whose losses would be collected again to have a better estimation of this loss surface. However, as the search space is infinite in this case, despite convergence guarantees, Bayesian optimization is susceptible to how well bounded the problem is. To encourage a faster and better convergence speed, we introduced the learnable search space approach of Perrone and colleagues, where they try to minimize the volume described by the hyperrectangle of the bounds in the optimization process. This would allow us to refine the bounds at each iteration and improve convergence speed. So here you would find the whole algorithm all together in a federated setup. And on the right, you would see an idea of what is the result after optimizing the bounds at each iteration. So as you can see, having a more localized search space that where the minima is. For this, we used 87 MRI measures using the free software Recon All pipeline in its version 6.0, for a total of 2,369 participants, which emulate for institutions. In the first task, we tested a linear regression problem for synthetic and age regression using the MRI-derived phenotypes. And here we illustrate the R-squared evolution in the regression task for centralized federated averaging and our proposed federated Bayesian optimization approach for both synthetic on the top and real data on the bottom. Comparable results seem to have been achieved in this particular problem. And to better visualize this, the learned loss landscape was reconstructed with good accuracy in this convex case, as you can see in the parameter space. For the non-convex case, a control case classification was defined using the subset of participants categorized as cognitively normal or with Alzheimer's disease to make of this a binary task classification. The train test is illustrated on top, whereas the validation test on the bottom. In this setup, the optimization problem struggled more, even when we allowed each site to perform a partial optimization locally using SGD to guide the search. So noticing this, we decided to go back and explore the scalability of our approach in terms of the number of parameters to be optimized. The results showed, as remarked in blue here, that the method clearly underperformed with respect to existing approaches as federated averaging as the number of parameters increased. So we decided to stop there and conclude basically that despite the initial promising results, this may not be the best method for centralized optimization, unless under very low dimensional problems. So further exploration is still required, of course. And for instance, as found later by Dai and colleagues, variation optimization in a decentralized setup was actually useful for hyperparameter tuning, which is normally a problem with not a lot of parameters. And finally, I would like to walk you through the contribution to the creation of a common framework in federated learning for healthcare. We decided to title this project Fed Biomed, and we initially presented this project in the distributed computing workshop in MICAI in 2020, and it corresponds to chapter 5 of this thesis. So this project was born in 2018 as MetaImagen, where we were trying to perform a variability analysis on decentralized data by proposing a pipeline that included federated PCA jointly with a federated confounding correction method. In doing so, we realized that there was a lack of common frameworks for federated learning in healthcare. With this in mind, we started Fed Biomed in 2020 as a full open source and production-ready framework. This project continued growing, integrating new functionalities to be what it is today. More specifically, my contributions to this project, we can say, were the first, the conception and creation of the project in terms of software and architecture, and secondly, the development of the core in its first and second versions, which additionally include more interoperability with respect to the existing libraries like PyTorch, and a data management frontend for the institutions to have. From version 3.0 on, I was rather participating in the development of particular features, and also we could say as a consultant more than a developer. So back during its conception, we realized that while general federated optimization approaches and frameworks that were being developed at the time, they used to lack either the deployable production-ready features, or they were constrained to work only on privative hardware. This was the case in particular of NVIDIA Clara, as it was closed source at the time and tailored for their hardware. PySift, on the other hand, was still an early and stable project, and it was more designed to be focused on differential privacy, multi-party computation, including homomorphic encryption. And CoinStack, which was developed at the same time, but it lacked interoperability at the time with existing deep learning libraries such as Keras or PyTorch or scikit-learn. With this in mind, we decided to propose a framework that was first containerized to allow to overcome software and hardware heterogeneity, and with this enabling reproducibility, that was extensible by supporting new federated learning approaches, existing libraries, and not being restricted to only gradient descent methods. And finally, that was standardly secure. This means including features like encryption, authentication, data, and role management. Fed Biomed has had multiple contributors as for today, and nowadays is mainly maintained by the SET engineers team at INRIA here in Sofia Antipolis. So the workflow we decided to define within the Fed Biomed framework is as follows. So first, we need to set up the infrastructure, including the nodes that in our case would be the hospitals, and a central server that, as I mentioned at the beginning, would coordinate the communication. So secondly, each institution will need to select which data will be made available for training, and also assign tags for each study and each modality of the data. For this, we designed a system of unique hashtags that are then used by the researcher in step 3, where the researcher has to define a training plan for starters that includes the model architecture, for instance, a pre-processing pipeline that is either observation-wise or federated, and of course, if it is necessary to define a privacy mechanism like differential privacy. Secondly, an aggregation scheme is required and is normally selected amongst the provided options, such as federated averaging or federated prox. And in some particular cases, it is necessary to have to define a sampling strategy. This is particularly useful when handling a large amount of institutions. Once the federated experiment is deployed and approved by each institution, the researcher will count on standard tools for monitoring the evolution of the model and thus debugging in the process. So in parallel with this with this project, in collaboration with the RAI and colleagues who identified the need of real federated datasets, we co-created FLAMBI, which is a repository with multiple datasets of brain imaging and other types of biomedical imaging that come naturally from multicentric databases and that are of public access. The goal of this project was to provide researchers with a simple data loader that would make the data available already in a federated and unified framework, like in our case, FedBiomed. So we contributed to this project in particular with the creation and integration of the ICSI database, a multicentric data set of brain imaging, jointly with other sets that were developed by other contributors like Chameleon 16 and TCGA that were introduced and put and compatible within the core as well with of FedBiomed. So we can say then that we propose a core that is now a growing initiative of a common federated learning framework for healthcare that accounts for system heterogeneity, data governance, integration with data sources. In particular, we can talk about BITS, NIFTY, DICOM, etc. That has already a standard security integrated, as I mentioned, encryption, and there is also tunneling. Additionally, we integrated multicentric databases for benchmarking, and FedBiomed, of course, continues to grow today towards the translation of federated learning methods to healthcare. So concluding this presentation, we can sum up some contributions, the publications as products of this work, and some perspectives, just to sum up. So first, we contributed to the field of harmonization by proposing and exploring 2 methods that will allow for global harmonization on decentralized data, accounting for non-linearities and without requiring any a priori information on the covariate effect or interactions between them. Secondly, in the field of federated learning for healthcare, we contributed with FedBiomed, a common framework for federated learning in healthcare that is open source, transparent for everyone, and that is production ready. And from this thesis, 2 publications as main author have been made, as mentioned before, and some collaborations also were part during this journey, including workshops in MICAI, human brain mapping, as I mentioned, ISB, and the issue of datasets and benchmark tracks of NeurIPS, and of course, IPMI. So amongst the discussed perspectives, I would like to focus or to sum up with these two in particular. It's worth considering a thorough extension of these methods to the image domain, and more importantly, clinical validation, as this is where the final impact is. And an example of a target which we have had in mind since the beginning of this project is, for instance, the Enigma consortium, which has around 70K patients distributed all around the globe. So I would like to thank every actor that made this project possible, and I would like to thank you all for being here. Thank you.
Thank you, Santiago, for respecting the time. So now we will proceed in a standard way with questions, and the two first person who will ask questions are your reviewer. So I propose to begin with James Cole, and after I will take the lead.
Okay, perfect.
James, the floor is yours.
Thank you, Jean-Francois, and thank you, Santiago, for a very nice presentation. Just because this is the first time I've done a thesis defense in France, so the idea is that I have the floor for a while, and then you take over. Is that right, Jean-Francois?
Or... You can take the time you want. Let's say 15-20 minutes or something like that, or less. It's depending on you.
Because I mean, the system in the UK that I'm familiar with, it would be more like both the reviewers would go through sequentially the thesis, you know, more in tandem. But I mean, I don't mind really.
No, it's not the same, but
fine. Okay. Well, there we go. I'm learning something. Okay, so Santiago. So I mean, you can probably stop sharing your slides, or I don't know whether that's.
Yeah, unless you want to reference them, I can stop sharing. Is everyone okay with it? Well, otherwise I can come back. Otherwise.
Okay.
Otherwise.
Sure. Okay. So I guess we should probably start with chapter 2. So you mentioned it briefly when you were presenting your results, but the when you compared the root mean squared errors with the mean absolute errors, the mean absolute errors were much more kind of consistent between them. So do you have, why do you think that might be? And yeah, what's the extra interpretation of the root mean squared error?
You mean like how similar they were across methods, right?
Yeah, exactly.
Yeah. So basically, like the error estimation is very attached to the range of the feature. So basically, depending if we are talking of something that moves between 0 and 1 or 0 and 1,000, the mean absolute error is going to be very sensitive to that. So I think it was probably more linked to this, and this is why we decided to do the root mean square error. And also, I think it was linked with the fact that I was like also thinking about it, the terms in the terms of if it is a good metric actually. Because in young populations, let's say, like if the function is, the differences are small, let's say estimating the age and having a mean absolute error of 1 year, with someone who is 60 years old, it's okay, but with someone who is 30 years, it's already like a large percentage. So I think it was related to the fact that the feature had a range that was very small. So I don't know if it was.
Yeah, that sounds reasonable to me. So yeah, I was interested in the. In fact, it might be useful for you to put your slides up actually. So I was interested in figure 2.4 with your Bland-Altman plots.
Okay, so coming here. It's not gonna be full screen, but of the Fed combat, right?
Yeah. So chapter 2, yeah, so a bit earlier than that.
Yeah, this
Yeah, here
one.
we go. That's the one. So my understanding of this is that there might be a sort of, if you look at where the 0 line is, there might be a sort of systematic underestimation
We could say
going on.
yes. Mm.
Yeah. What do you think's driving that?
Yeah, this is something that I actually I literally I couldn't explain, and because I don't know if it has to do, yes, as you mentioned, just an underestimation of the method, but it happens with all of them. So which is, and it also can be that there is a bias already, that the distribution maybe of the mean effect is already tailed. So that maybe having a reference would be better. I don't know if, because in combat, you can either have a mean representation, or you can take one site as a reference, for instance, that you consider is less biased. So probably it's also due to this.
Right. And in terms of kind of downstream applications in kind of clinical contexts, which is of course kind of the point, the overarching motivation of this, what impact might that sort of bias have, and is it worth thinking about the difference between the bias and, you know, shrinking the distribution, like having a more uniform, harmonized distribution? That makes sense.
Yeah, but clinically speaking, like it would help to avoid reporting maybe effects that are not there, or actually to identify effects that we are basically missing, I guess. But yeah, that would be basically.
Yeah. Okay. And would there be some kind of additional steps you think you could use kind of to check for these potential underestimations, or like other ways of addressing it?
Yeah, of course. Yeah, I guess of course there is clinical validation, like having let's say, for instance, I remember after harmonization, some features can be even negative. So if the distribution, for example, if it is overcorrected, the data is what I'm trying to say, it doesn't make sense, for example, having volumes of -1 or -2, because it's a physical measure. So this could be an indicator of underestimation, or having like heavily tailed values that are basically either null or very low, I guess. So of course, clinical validation would be the right approach to see if the measure is actually mean with respect to what we know so far, or yeah.
Yeah, great. So you made a very interesting suggestion. I think it's an important point, that extending these kind of methods to voxel level or image level things would be really useful. Have you thought about the kind of practicalities involved in actually doing that?
Yeah, so in the case of the multilayer perceptron, but in the case of combat, it was extended to, it's been already extended to voxel-wise harmonization, and basically each voxel is considered a phenotype. So the intensity is approximated by the combat model, but there is no awareness of the neighborhood, for instance, and this is done to optimize, because it's a very high dimensional problem. It requires a lot of time and iterations. They use the brain mask in order to make it only in the areas that is relevant. In the case of the multilayer perceptron, it would be like a bit challenging, I guess, in terms of dimensionality, because we would be talking in brains. It's in the order of hundreds of thousands, or even sometimes millions of voxels. So this could be challenging. But in the case of the variational autoencoder, which would include convolutional layers, it could be probably more more interesting to see. And so it's, I think, I don't know if it was clear.
Yeah, no, that makes sense. Thank you. So the main kind of idea that you're sort of the novelty of this aspect in this chapter is the use of a multi-layer perceptron instead of a GAM for automatically essentially modeling the non-linear nature of it and automatically modeling covariate interactions. What's obviously you're more likely to have overfitting, I think, with a MLP compared to a GAM. So how can you kind of control that?
Yeah,
side
so
of it?
yeah, so there are several techniques in the case of multi-layer perceptrons. So we decided to go for a cross-validation scheme, basically, where we would stop the training as long as there was no improvement in the validation loss, but there was an improvement in the training, which is more or less trying to find the Q point, the point that represents the best compromise during the training process. But there are also some techniques like dropout or just adding regularization on the terms, as we suggested in the second model, following a Bayesian approach on the weights or things like that. So even though they would complexify even more the model, but these are strategies that are but nowadays introduced in the field of deep learning to account for that. But as in our particular case, we decided to go for a cross-validation scheme, and it seemed to work good enough.
Yeah. Okay. Thanks. So moving on to the next chapter, chapter 3. So the chapter was entitled about mixed effects models.
Yeah.
Obviously, the main focus really is about conditional variational autoencoder.
Yes.
Can you reconcile that for me, please?
Yes. So that was basically the original inspiration of what we did afterwards, because at the beginning, as I was mentioning, sorry, let me try to go to that part. At the beginning, we were trying to consider the combat model more or less, but considering also a random slope. So instead of just considering a random intercept. And this was the first approach we took. You may not be able to see that. So this was the first approach we took. So try to get a generative model that would be account for random effects within the model. And then basically the conditional variational autoencoder does it without having to assume any prior on it, and it does capture the let's say random effects in the parameters. So that's why the chapter is entitled like that. So probably would need a bit of rephrasing.
Right. So obviously you have to train the autoencoder when you're learning this. How do you think differences in the hyperparameter optimization could influence the kind of downstream harmonization?
Well, in our case, we used actually a hyperparameter, like it was tuned, the model, for this problem in particular. But the hyperparameterization basically would allows us to have a better estimation of the data distribution at the end. But as well, it would make it more prone to overfitting, I guess. So be able to reveal.
Do you think you found the kind of global minimum of the modeling the distributions, or could you have sort of different local minimums that perhaps give you a slightly different way of harmonizing the data? Does that make sense?
I'm trying to. Could you repeat that, please?
So obviously, when you train a model, you end up with a solution, and you try to stop it before it overfits, basically, and that may be the global minimum in terms of the best way you could alter the weights and biases to explain whatever your outcome is. But obviously, knowing whether that's the global minimum is not always possible. And, you know, it could be that there's a sort of local minimum that you're in that may be quite near the global minimum in terms of the final loss, but it might not be that near in the parameter space. So you could have two local minima that sort of appear equally good, but may not have the same combination of weights and biases. Could be quite different.
Yeah,
That's kind of what I'm getting at. And then that could lead to a different way of conditioning the data. And I wondered whether you thought about that and if there would be any way of knowing how that would impact the harmonization at the end.
Yeah, this is something that sometimes we resigned on, I guess. Like we don't pay that much attention, but it's totally a field of research on how to ensure whether it is the actual minima or not. So this I wouldn't know how to answer probably, because optimization is a bit out of my field. But I know that some people try to account for this by adding like a mixture of experts, I think it's called, where basically they try to train multiple models for the same task and try to combine the output of them, I think. But it's more or less what I've seen out there, but I wouldn't know how to answer.
Yeah, I mean, there's not an obvious answer to be honest, but I just wondered if it's something you considered when you were actually doing it. Okay, so you've obviously presented in this chapter a whole range of interesting results. Could you view some other sort of benchmarks for how well this works to compare it to?
Other benchmarks
in terms of different ways of doing harmonization. You've obviously got the unharmonized versus the after harmonized, but in terms of other ways you could have harmonized the data as a sort of more straightforward approach.
Yeah, so apart from the one we proposed, which is try to bias trying to reconstruct a target function, you mean?
Yeah, exactly. Because you're comparing it to kind of before and after harmonization, but obviously, as you point out in your earlier chapters, there are other ways of doing harmonization.
Exactly. Yeah. So it's so for in the case of images, I guess there could be a similar procedure where you have like trying to estimate, let's say, the actual brain before adding some bias in it. But I think the challenge and also what needs to be observed with special attention is the fact that we are biasing the data following the models that we are trying to use to harmonize. So maybe focusing on challenges as the OpenHB, which is a regression task. So trying to regress H is what I'm trying to say. So we're trying to regress H is probably one of the approaches that could be done to evaluate if these models are accurate or not at harmonizing, because we know H is a less biased of a measure, let's say. We can. So
yeah.
I don't know if it does answer your question.
I was kind of more getting into sort of could you have added in another technique here to compare it to? So not an outcome that you're trying to predict, but more a sort of different method, a simpler method, and see how that influenced things. But I think, you know, I get your point that you've kind of already looked at that earlier. So that's fine. Okay, so moving on to next chapter 4 is Bayesian optimization. So yeah, I was interested. I think it's a really interesting idea, but I mean, I've done a bit of work with Bayesian optimization before, and I think it's quite well known that it's doesn't scale very well. And I wondered whether that was something you'd considered at the start, or whether that was something that just sort of became apparent as you were looking at the data.
Yeah, it was definitely the second. Yes, it was definitely the second. It was something that I personally discovered later, and we tried to approach this. And for this, I wanted to make a particular remark. So we try to approach this by relying we'll try to minimize you because I'm with the audience here as well. So by relying on two methods, and the first one was this method proposed by Kutajar in 2017 that tries to precisely use gradient descent for the optimization of the Gaussian processes. So we try to find alternative methods that would allow us to scale up in the estimation of this response surface. And so we explored this one, but the problem is that it had the trend to overfit the points. And same happened with this approach of black box matrix matrix inference, which is basically included in the GPyTorch library, and tries also to improve the scalability of Gaussian processes by relying on GPUs, for instance, reducing also the complexity of computation. So we tried these two, but still O square was is still complex enough to what we were trying to do.
Right.
We were, yeah.
Do you have to go back to the kind of practical long-term use of this kind of thing? Do you have an idea of how many parameters would need to be optimized in a sort of typical study? Because you had a whole range from sort of 1 up to the thousands, I think.
Yeah, exactly. So normally these approaches are in the order of tens of dimensions. Yes, I think.
Right. Yeah, I mean,
if I can recall correctly, it should be in the order of tens.
So thinking about Enigma, which you mentioned at the end as a sort of future direction, I assume you know what the sort of typical input to Enigma models is.
Yeah, it's in the order of hundreds, even sometimes thousands, depending on what you are doing. If it is shape, I guess it's even higher.
So Enigma, most typically, Enigma would use the output from recon-all, particularly to look at the Disikian-Kaleni atlas, is probably most commonly used, along with the subcortical segmentations, and that gives you about 100.
Yeah, it's in the order of hundreds, I remember, yeah.
So just looking a bit more at the sort of experimental results, I was wondering, could you have used, maybe I'm sorry if I misunderstood this, did you use a non-federated Bayesian optimization version as a benchmark here?
No, for this one we went straight away for the federated optimization. We saw that in the centralized it has been already proved, so we decided to move on, because we were not like trying to build on the method itself, but trying to rely on it for a federated setup.
Sure, but do you think it would have worked in a similar way had you just used it? Yeah,
absolutely, because the only thing we are changing is the way we sample. It's not the estimation of the Gaussian process is done in the same manner, either centralized or not, with the difference being only the way we sample from the parameter space. So we just ask the clients to give us the loss, and we try to reconstruct the loss. So it should be the same.
But you did use a sort of centralized stochastic gradient descent in some of them, I think, to some of the figures. Is that right?
Yes, absolutely. Yes, this was to actually have a sort of ground truth, because as you mentioned, like that we cannot perform best, or we were not hoping to perform best than gradient descent or federated averaging, let's say.
Okay, great. So then just moving on to if I've got time, Jean-Francois.
No problem.
So I've mentioned briefly about chapter 5. So clearly, this has been your major contribution here has been the sort of software engineering that's the impression that I got, is that you've led a lot of the sort of development of this, which is a huge piece of work. So I think you should feel really proud of yourself for that. But just sort of touching on the kind of experimental results, do you think could you have thought of ways of taking that further? You include some data on some real and some MNIST data and some brain imaging data. Do you think you could have taken that further? Did you have other plans for how you could have analyzed that? To
realize what? Sorry.
To analyze the real data to kind of show that it this works in practice.
Yeah, but in practice, so I didn't mention it here during the presentation, but in practice we trained a model using brain data as well, just to compare it with respect to the existing methods, and we went for a variational autoencoder just to show that it was working. And we did it with MNIST in that case, because it's a common benchmark to do, but we also did it with brain data. I think your question was more related to if we benchmark this somehow, right?
Well, it's kind of about the benchmarking, but it's also, I think you were just looking at the reconstruction really, rather than kind of prediction of clinical outcomes or things like that. It was more like I was wondering about.
Yeah. Okay. Yeah, but like right now, there have like within the documentation there are multiple experiments available, and they focus on that. But yeah, during the publication we didn't emphasize that much maybe in the brain application, maybe as thoroughly as we could have.
Yeah. Okay. I think that finishes my points that I wanted to raise. So thanks, Santiago.
Thanks
I'll
to
hand
you.
you back to Jean-Francois.
Thanks to me. So it's up to me now. So just to begin with, Santiago, I would like to say that I really enjoy your manuscript. I think I mainly read it in a plane and I did not fall asleep, so it's a good point. I was impressed by the fact that your contribution at two levels, the algorithmic ones, but also the software engineering ones, which is usually time-consuming and difficult to do at the same time. So congratulations for that.
Thanks.
I'm not an expert of federative learning, so I probably missed some of your contributions, but I will ask you my own questions. I will begin with the very general ones. I mean, it's not completely clear where the field will go in the next years, but I wonder what's your feeling about the fork between harmonizing features or harmonizing images. Where do you think we will go, and what's the interest of both strategies?
What would be sorry, I missed that last part.
Well, I mean, what do you think about the two strategies, the ones which is consisting in harmonizing raw data or harmonizing features that you extract from the data, the goods and bads and the two strategies?
Well, of course, harmonizing the images, it can be cumbersome as the dimensionality of the problem becomes already very high. If we are talking at the voxel level, training these models would require, of course, more resources. Could be more prone also to overfitting, for instance, or to introduce artifacts. So this is why I may be more careful when it comes to trying to harmonize images, I guess. Whereas the features normally, like the risk is more on the pipeline side, either estimating properly the measures, the volumes, and the cortical measures. So I think it would make maybe more sense on that sense, at least in my opinion, I would say.
Okay.
Yeah. Then recently we were discussing that there was a paper that also is trying to reevaluate the concept of harmonization, as a lot of recently proposed methods seem to struggle in particular tasks. So I think that's worth checking. And it was a paper that we saw with Andre, I think it was this year or last year. That so yeah, so probably we would even need to redefine the harmonization itself.
Okay. I have another general question. If you consider imaging modalities which are multi-channels, for instance, diffusion imaging, this can be multi-channel, of course, at the level of acquisition, but also at the level of the features. You could get, for some specific region in the brain, several features describing the diffusion process. Would you set up the harmonization framework the same for this kind of modalities, or this would require something different?
I think, yeah, in the case of diffusion, as far as I'm aware, at least for things like fractional anisotropy, I think it's the standard linear model is what it's used to harmonize the different scanners. Yes, as far as I can recall, and so in our case, we would proceed the same way. So each voxel with the fractional anisotropy inside would be harmonized, considered basically a phenotype here, I guess.
But don't you think if you had several features like fractional anisotropy and all the microstructures that you can get from diffusion, do you think you should add something in the model?
Some, if we would add, sorry, some.
Would you have to add something to preserve some of the relationship between the features?
Yeah, precisely where we were trying with the multi-layer perceptron was that trying to see like how they would interact. Although, no, I see your point now. Yes, because basically we'll be doing the prediction for each modality. So in this case, the conditional variational autoencoder would do better because it would try to model the joint distribution instead. So
okay.
So yeah. So yeah, because in the other case, in the case of the combat, each modality, let's say, or each feature would be considered independently.
Okay. And generally, thinking about the combat way of harmonizing data is dealing with a few covariable. I always wonder what happens to covariable that you don't inject in the process.
That's
whether I mean, you've been discussing with James about overfitting. Overfitting could just kill the effects that are of interest on other variable. Could you imagine a way to test this kind of behavior, or to add some kind of regularization, whatever could protect some other effects that are not in your models?
Yeah, but there is always regularization on the parameters. So trying maybe to give more priority to some parameters with respect to others in the optimization process. But yeah, this is an inherited problem of not measuring the covariate, I guess. So not having this effect would lead, of course, it would be captured by the noise model unless it's highly correlated with the batch effect. So anyway, like even if it is not observed, I guess it will be captured by the noise model, these differences. So as long as there is not a lot of correlation between sites and the missed covariate. I don't know if I'm making myself clear.
I don't know what's the answer to that. So I was just willing to know your feeling.
No. What I was trying to say is let's consider like just a cohort that is fully masculine and the other one that is full of a female population. So the two sites and the sex covariate is highly correlated, let's say. So in that case, the effect would disappear, of course.
Yeah.
But if it is mixed, then even if you don't have it, the noise effect would be able to capture, I guess, a bit of those differences, because we are trying still to keep the shape of the distribution anyway. So I think it would be maybe not, it wouldn't be as good, but I guess it would try anyway to capture this effect.
Okay. I have a question about what lead you to aggregate autism dataset and neurodegenerative dataset.
Yeah,
I'm
yes.
really curious about that.
Yeah. I saw the comments. So basically, the idea was just we were wondering like what would be a good way to exploit like the whole cohorts, and so we decided to see how typical and atypical trajectories would behave. Typical being cognitively normal people, and atypical any other patient that was considered either in the spectrum with Parkinson's or Alzheimer's. So it was just for the sake of comparison, but of course, maybe in a clinical setup, the comparison would be different. And also, this was done because the estimation of this function, the covariate approximating function, gets better as you add more data. So the more variability you have, or the more data you have, because the better the estimation of these effects is. So this is why we try to introduce this, like consider everyone basically.
But you did not try to harmonize the ABI dataset by itself.
Yes, yeah, we try to harmonize it, but considering as a whole site. It's true. Yes.
Okay.
Yeah. So probably yes. It's true that considering each site.
There was some issue at splitting ABI in different studies, or I mean,
No. Well, there were some because some sites are very small, but so that would lead, of course, to a poor estimation. So it was a choice, but of course would have made more sense to consider the different sites within each of the databases, because APNI as well, for instance, is also multicentric, even though.
Yeah, but ADNI is harmonized, at the acquisition level.
Even though the protocol is more standard across sites, yes. Yeah.
Okay. By the way, I forgot to say that your presentation was really, really clear. I mean, even better than the manuscript, I think. So congratulations for that. In some of the description you gave on the results, I discovered something maybe I miss or overlook in the manuscript, which is these trajectories where you show, for instance, different in trajectories in early days in the hippocampus or things like that. There's something like that. I was really disturbed knowing that the young subjects are from the autism studies, and you infer something about hippocampus. I was a bit lost. Could you clarify what you noticed?
Yeah, so yeah, I was trying because this was something that we weren't able to do at some point. It was basically trying to make sense a bit from the learned trajectories. So here, what I wanted to show is basically like in the literature, what is reported for autism is is this one. Well, yeah, this is still under discussion whether like kids or young population within the spectrum have a lower volume, lower hippocampal volume, whereas the adolescent and adult population seem to have, and this is something where they agree more in the state of the art, or at least in the literature. Sorry, we'll try to zoom up. Cannot zoom up. Sorry, they do agree that there is an enlargement of the amygdala for teenagers and an adult population. And this is something that I found interesting to mention, maybe as a discussion point, because this is an effect that is captured by the model that is given by data that was provided from an autism cohort. or a cohort with autism. So these blue ones are basically ABIDE, whereas the ones on the right are basically neurodegenerative diseases. So we are able to see the two differences, despite the different nature of the syndromes or diseases as well. So in early stages, we see the differences as reported in the literature, and as well for the elderly. So this was more or less the remark that I wanted to make. And of course, this is what I was mentioning as well. I was mentioning is the requirement of clinical validation.
Okay. There's a situation that occurs often when people try to aggregate data from all kinds of studies. For instance, in the context of Enigma, it's the evolution of the software that provide the features. You can have around the world a lot of data sets, but they stem from different versions of the softwares. Did you consider playing with that or playing with the parameters of the software to see whether you can correct for these effects?
Yeah, we didn't because it's also something that you could try to harmonize, I think, arguably. And but we were lucky to have the whole 9 cohorts with the same version. So so we decided to go for that and instead focus on the side effects. But yeah, sometimes people try to harmonize, yes, that part, like the version. I don't know if it is a good idea. I think it's arguable, but some people do.
I remember something in your manuscript where I didn't understand the idea. I think if I understood clearly that you suggest that the Bayesian optimization would generalize better. It's something that was maybe one of your motivation, and I did not understand the reasoning there.
Yeah, so there are some in the original definition of the method. They give some guarantees of convergence that were tempting actually. So that's why we ended up using it. So they guaranteed not to end up trapped in local minima. Of course, when t tends to infinity. But the method itself, by definition, cannot end up in a local minima, apparently. So.
Okay, I have a last question by curiosity. I mean, what's the number of users of the Fed Biomed environment that are not relying on the INRIA team? Is there already some people experimenting with it elsewhere in the world?
Yeah, so at UCL, there was Neil Oxtoby with the Passion project who were trying to implement Fed Biomed as the framework for a classification problem they tried to define in Alzheimer's. And here we had Hospital La Casaña, who work on prostate cancer segmentation, and they have also been using the framework. And right now the initiative is going a bit larger, so more participants, I think, are joining nowadays. This would be more of a question, I think, for Marco. He knows a bit better now. He's been closer to the project.
And do you plan to be part of the future of this story?
But right now, I'm actually looking to move on and try to experiment new things. So sadly, I had to stop to collaborate within the project because I needed to move on with the thesis. And now, like, I'm moving on to new stuff. Yeah.
Okay. Thank you, Santiago. So now I will move to Switzerland, I think, to Jonas Riccardi for the next round of questions.
Thank you very much. I'll try to keep it brief as well, because indeed there's a number of things that have been discussed. So first of all, Santiago, just to say that it's a very nice work and you're working on a very important topic. So this is great. Being in a hospital, I really need advancement on these issues. The manuscript, I agree, is very well written and illustrated, as was the presentation. So this is always nice to see this. And what I liked is you're doing a comprehensive way of comprehensive exploration of the various ways in which we could do federated learning, because I mean, there's a number of things and you've really explored the topic comprehensively. So this is a nice one. What I really loved is the fact that you're not taking one data set, not two data sets, but 9 in most of your experiments. So this is really cool because this is indeed one of the things that it's very easy to make things work on a toy data set, but basically you took all the open data sets available. I didn't see UK Biobanks, a bit disappointing here, but that's okay. Next
we didn't have access.
And yes, and indeed, as Jean-François said, it's actually very nice also to see all of this translate into practice with an implementation and open source. And it's very nice to have the INRIA team, picking up what you started to develop. So this is really, in terms of impact already, I mean, you can stop there and, you've done your part for humanity. So this is great. So let's talk a little bit again about this image space. So James mentioned this and Jean-François mentioned this. I want to go back to this image space harmonization, because we've also been working a bit on that with ups and downs. So first, on the one hand, you mentioned this voxel-wise harmonization that maybe is worth doing, but at the same time, as you discussed with James, it's very weak because you don't really model the context. So I think it's kind of like doing a voxel-wise GWAS or this kind of analysis where you're basically assuming a mass univariate model for something that has a lot of spatial autocorrelation. So probably not necessarily a good idea. So on the other hand, you could also do the harmonization in the image. So my question is, you've focused on the phenotype, but the phenotype, which in a sense, is this image derived phenotype, like volume of the hippocampus or something from free surface. But the fact that hippocampal volume is up or down could be due to a ton of things, right? It could be due to the coil that you're using, to the magnet strength that you're using, to the sequence that you're using, to the technician, because some technicians like to put a little pillow under your heads, the other ones don't. So you have a huge amount of it. All of this, you're now losing this information because you're focusing just on whatever free surface is giving you. So how can you justify actually working on the phenotype? Like, how can you get all of these like acquisition factors, for example? Can you model them extensively? What can you do if you're not doing image-based harmonization?
I guess if this error, let's say, for example, the one of the pillow is systematic enough, I think it will be captured. It should be somehow captured by the harmonization method. But let's say if it is not, we would have to move back again to protocols, to defining and following protocols, I guess, because it's the only way that keeps things as harmonious as possible.
So harmonization you want to do kind of like as in ADNI, right? So in ADNI 3, for example, you have like all these standard protocols. So that, but despite this, you still have hardware issues, right? Even if you have the same model, you might have a number of others. So do you think is it possible that with the type of approach you're doing, like from kind of a linear model perspective or a regression perspective, let's say from an already extracted phenotype, do you think it's possible to actually have as much richness as like an image-based and as an image-based approach?
Well, I guess it depends on what you're looking for. If you're of course trying to identify the regions that are within an atlas, let's say if it is relevant for you, the localization within the brain, I guess, yeah, following a phenotype approach would be okay. Then otherwise, if you want to focus on the more granulated, let's say like more fine differences between brains, like I don't know, control versus case, then probably going for a brain-to-brain comparison or to the image space would be better. I think, yes, yeah. I don't know if that answers the question.
Yeah. No, I think it depends completely on the scope, for sure. Yeah, but already I think with adding the nonlinearity is already kind of a very good step towards like what you want. in terms of like the Fed combat algorithm, because I noticed you basically you're doing everything you're doing is kind of wrapping within or around Fed average, right? And so one of the concerns I have, which is not necessarily about Fed combat, but Fed average, is let's say you have this case, so you have this aggregation, right, which is the number, the scaling factor for the weighting for each site is number of cases in site I divided by number of cases in total, right? So it means essentially what it does is the weighted average means the small sites have way more impact on your gradient update, right, on your average of your parameters. Now, what happens if you have a site that is super different, but also happens to have, let's say, 10 times fewer cases than the others?
Yeah, so the contribution is going to be less when it comes to the estimation of the covariate function. The contribution is going to be less, but in terms of the shift, it's going to be like the shift and the scaling factor, they're going to be adapted anyway, so it's going to be captured, at least these two parameters. So in terms of shift and scaling the variance, there shouldn't be a problem. But in terms of the estimation of the covariate effects on the phenotype, this center or this site that has fewer observations would have a less contribution during the learning process. And the question that I would bring back is whether it's good quality data or not, because you can have a large data set that is rubbish and a small one that is high quality. So that could be also a criteria to consider when assigning who contributes the most.
So how would you do this, for example, within your framework?
Yeah, this would be a more heuristic, I would say. I don't know if there is a smart way to do so. Nothing comes to mind right now, but it's something that it's worth considering, maybe.
Yeah, because I think in your case you're doing essentially your whole use case, I think, is built around kind of a meta-analysis, right? You want to learn something about your population in general. You don't care that much that the individual sites can then do good inference on their own little data sets, right? That's not necessarily the point for you.
No, not necessarily. No, you want it to generalize as much as possible.
Yeah, so this brings me to the next point, which you say, like in your chapter 2, that hypertuning is out of scope, and we discussed a little bit about hypertuning, and we said, it doesn't scale necessarily, but like in this situation, how would you do it, right? And this is also kind of in general, maybe I have a few more questions after that about how you set the number of local, like in this Fed average, right? You need to set the number of local epochs and then how often you go back to average with the global model, right? So that's one of the core decisions. So for example, this one, how would you, well, actually, this is one thing maybe I missed, but did you optimize this, or did you just say, we do 10 local, then we average, or how did you choose this hyperparameter, for example?
Did I optimize this? You mean?
Yeah, how did you choose let's say the number of local epochs you do before averaging, for example?
Okay, yeah. So for this in particular, only to give to get the closest results possible with respect to the SGD, we decided to focus on one epoch. And the reason to do
one local epoch, then average, one local epoch, average.
Yes. Yeah.
Okay.
Yeah, and the reason to do so is because basically doing one epoch per site and aggregating the weights is equivalent to do one epoch of gradient descent, mathematically at least. So this is why we decided to stay with that setup, and we didn't dig further. And this was only to try to get as close as possible as it would be for a centralized setup, if I'm making myself clear.
Yeah. Okay. Yeah. Okay. Of course, to compare, because you could also do like a few global you could distribute this in a number of ways, right? You could also do a few global epochs and then redistribute, and you could there's a number of ways you could have the same number of epochs overall, right? To be comparable with the centralized models. And this is always something that is a bit tricky. I'm not sure how to tune this either, because it becomes already the local tuning is tricky. And then if you have this hyper tuning, I think it becomes even more tricky. Okay, so to finish, maybe maybe if you go to slide 25, this, you had like big numbers on your slides. Yeah, let's say this one. Let's say this one. That's fine. Yeah, this one is good. 25.
Yeah, I don't know if it, I don't
No,
know.
it doesn't. I'm still seeing 24. So next one. Yeah, I mean, it doesn't matter much. That's fine. That's also illustrative. So the one thing I was missing a bit in this presentation is you're showing. So this you're showing nicely, like qualitatively. You're showing nicely, like qualitatively, the results, let's say, between your atypical and your healthy controls. One thing I was missing a bit is a notion. So you show that you can harmonize, which means for synthetic data, it's very easy to show if you're doing well or not, because you can compare with the ground truth. One thing I'm kind of missing here is a notion of how well you preserve the, let's say you want to discriminate atypical versus healthy controls, how well you preserve this separation. So is it because the harmonization, you could have very good results, just put everybody to 0 and then you have perfect harmonization, right? So that no site difference and you're done. That's great. But
yeah.
how do you have like a metric to show a little bit this notion of discrimination? And I had the same question, by the way, afterwards with a VAE. Like this is a bit something I was missing in the paper. Maybe I missed it here as well.
Yeah. So basically, what the standard benchmark that we started doing at the beginning was try to identify the site where the observation came from, using a classifier on the feature space.
Okay.
The problem here was that it's highly correlated, for example, with age.
Yeah.
So basically, you could identify the subject by just using the age. You could identify the sites. So that's why we didn't report these results, because they only make sense when the cohorts are distributed in an ID fashion. So when the cohorts are very similar across themselves, across sites. So if you have cohorts that are within the same range of age, let's say, so then this is why we didn't decide to report this. But of course, one of the things that we could do, and that we realized later in this challenge that I showed, is age regression. So being able to better regress age after harmonization, and this is probably the benchmark I would go for afterwards if we want to compare these methods.
So okay, so you want to show that you can, okay, so you have basically better age prediction. Okay, yeah.
Exactly, yeah, because age is an independent variable across sites.
Okay, yes, okay, yeah. Okay, all right. Okay, so let's move, so CVA, yeah, let's skip over the CVAE things. Let's go to the federated black box optimization. So again, I like the multi-data set, and that you have like nice benchmarking and centralized and fed average. Could we go to slide 46? Because this one I was really scratching my head. Also in the manuscripts, that was I guess yes.
I can see why. Yeah.
I don't see the big.
I think there is a problem with the sharing the screen.
Okay, well, but never mind. Okay, I mean we maybe recall it.
Now it's better.
Perfect. Okay, so I mean, there's a number of things that are a bit puzzling for me here. Just from like looking at the loss over the iterations, that's kind of not exactly what I'm used to looking at. First thing that is a bit weird here is if you look at the training set and the test set, you seem, I mean, I don't have like a proper metric of like confidence intervals or whatnot, but it seems like your training accuracy, so the top one is training right, and you're around 0.7. And then the testing, you're around 0.8. And I'm kind of used to seeing the opposite. Am I reading too much into the plot and it's not that different because you have wide confidence intervals, or is there something weird happening here?
You mean why it's going down, or why?
Yeah, I mean, no, why is it higher? Because it seems to be lower in the training and higher in the testing.
And
right, because it's around 0.8 and the other one is converging around like 0.7. If you look at the blue guy, the Bayesian optimization.
Yes.
right?
Oh, yeah, yeah, no, I hadn't remarked that. Yeah. If there, yeah,
Because typically, you know, you overfit and then you can get pretty good in the training and you show the performance and that works fine. And then in the testing, you kind of have a drop because it shows that you overfit, but here it's the opposite. So you're kind of not overfit, so, which is great. I mean, it's great for performance, but I really don't have an idea why that happens. Or indeed, if it's a real effect because you're not showing the confidence interval. So I don't know if it's actually reading too much into just a point estimate of the performance.
Yeah, I remember in this one we used a whole, I think it was, did we use no, I would have to verify that, but I would be lying if I give the answer. But yeah, it's a particular.
Okay, yeah, so this one is a bit strange. And
Yes.
then, yeah, there's this question of the plateau, but yeah, so whereas the centralized seems like indeed that's kind of what you want to see in the training, right? The centralized keeps overfit. I mean, you can overfit, it seems like if you continue a few more epochs, probably the centralized one can improve as opposed to the Bayesian, right? The Bayesian optimization reaches a plateau very quickly. The other one could improve, but this, yeah, it seems it's not clear to me because you mentioned that you had this low balance between exploration and exploitation. But
Yeah, that's why it goes down. That explains the behavior of going down afterwards.
Mm-hmm.
But the high peak over there being higher than the training set is
No, but that's a separate thing. But basically, like in the manuscript, you said I'm not so sure why you have this big plateau. Despite
the plateau.
Yeah, the plateau.
No,
sorry, that's like a second question now.
Okay.
So this plateauing behavior. Do you have more insight since you wrote the manuscript?
Yeah,
Or
sorry. Yeah. This is the way of the, because this is the evolution. If I actually showed like each sample, it would be extremely noisy, this curve. So basically in Bayesian optimization, what you do is just to report the best so far, and the best so far stays still. So basically,
okay. So it's okay.
It keeps sampling, but it doesn't.
It doesn't improve. Okay.
And that's why it's like it's very common to see like these flat lines constantly.
Okay. And then maybe the last one about this one is like, this is really puzzling to me to see that you can jump basically in one iteration or two iterations, you jump to the best and you stay there.
Yeah, and this is because we saw this behavior of taking like not being able to fit, so we allowed some local epochs before. So basically, the Gaussian process was fed with the optimized, the local optimized parameter. So instead of sampling, we would use the optimization locally, like a partial optimization.
Okay.
So that's why the first one is very high. Okay. And then it basically just becomes exploring, and it doesn't find what the best is, because it's either very well defined by the local optimization or it's just lost in the search space.
Okay, that's great. And then maybe my last one, if I can, there's a figure, this is a manuscript. I don't know if you showed it here, but there's like one of the figures for the Fed Biomed chapter, figure 5.4, where you show that there's one site and you show this norm of the weight vector, right? If you remember this plot, and one of the sites, the center number 4, where the norm of the weight vector is really far from the average.
Okay, so I'm trying to go for it. This is in the Fed Biomed one, right?
Yes. So I was wondering, so this is kind of the same questions I had before, because now the Fed Biomed, the idea is that you don't necessarily want to have a meta-analysis type thing. You want to have each site, maybe you want to have each site using the model on their own. And I was wondering, like this particular center that I'm talking about, like center 4, seems to be very far from the average, right? So I don't know if you looked at this, if you have an idea for the performance for this task on this particular site's data, like for center 4. Did you look at the individual performance in the individual sites, or you never looked at this kind of disaggregating?
No, we never digged into that that in detail, but yeah, like right now I'm seeing, and it would be yes, maybe worth looking as well.
Okay.
Yeah, because this was at the time we were proposing the framework, so we decided to focus on it more. But yeah, I see the point.
Okay, thank you very much. I think that's it from me. Thank you.
Thanks to you, Jonas.
Thank you. So now it's time to move to Andre Altman from UCL.
Yeah, I thank you, and thanks Santiago for the great presentation. The advantage of asking, the last in a row is that most of the stuff has been really covered. So I just first want to say you did a really nice job in presenting everything and the write-up, and it was a tremendous pleasure having you visit to do some of the work with you, and also having observed, how the whole project evolved from the very beginning. It's been quite a long journey, and it's really great. So I'm probably going to limit myself to one question out of more of curiosity. So in chapter 3, you're exploring the conditional variational autoencoder, and I was wondering whether you're only using site categories as conditions, but also maybe case control information as conditions in the whole mix.
Yeah. So in the conditioning process, maybe let me go back to this. So in the conditioning here should be here. Yes. So in what is here denoted as X is everything like is the distribution we want to keep. It's basically all the information we want to reconstruct, and this would include the phenotypes as well as the covariates. Okay. And the random effects, let's say, or the effects that condition this distribution and that we'd want to avoid or eliminate rather after. Yeah. Are captured by Y. So this is the site effect or the scanner effect. Then so they are kept, and this is why there is like this light blue in it. So it's basically okay. So it's the joint distribution that is trying to be kept. So yeah, it's inside it.
Okay, so it's part of your. Okay, yeah, that makes sense for the context. And the other thing, what we've noticed when we work with conditional variational autoencoders is, really you're working with categorical variables there, and the number of sites you could work with, I think it becomes a bit more inefficient, if you go from 5 sites to 10 sites to 20 sites. Have you experienced that?
I didn't, but
okay.
That's an interesting point. Yes, of course, if you have like 1,000 sites, then you would add at least 1,000 parameters, 2,000, I guess, yes, to the variational autoencoder, as the site effect is one whole encoded, yes. So I don't know if there is a smarter way to condition this process in the literature, yeah. So yeah, no, I didn't experiment with it. That's probably worth looking.
That's pretty nice. And also, I think the difference between, what you did with Fed Combat and this one is you basically you train a model trying to reconstruct your original data, and that, as you said already, variational autoencoders become a bit noisy. I think that's the kind of the drawback. You do get a reasonable adjustment. It's just not as pristine as with your other approach, I think. But
yeah,
I think if you have to pick and choose between, doing, I don't know, what would your preference be? Having, if you go voxel-wise, running, I don't know, 100,000 Fed combats, or going with one, conditional variational autoencoder. What's your feeling? What would be, done easier?
Easier is probably the variational autoencoder, but more like proper. I would say maybe go for a classical combat on the at the voxel level. And actually, that was a discussion we were having with Marco, in the sense of how, for instance, try to correct the bias effect, like the bias, but I mean the bias on the image, the bias field correction, what I'm trying to say, like how to model bias, the biased field effect on the image, but in a federated fashion as well, like trying to build this inhomogeneity mask that we normally try to reconstruct in the harmonies, in the removal of bias field effect, but in a federated fashion. And this is also something that could be worth exploring. If we want to harmonize, we would be basically doing two tasks at the same time, I would say.
That's it's interesting.
It's a totally different problem, but it could be also like worth considering.
Okay. Yeah, I mean, my questions have been, addressed already before, so that's very convenient. I think that's from me.
Okay, thank you, Andre. So now it's time to move to your supervisor. So maybe we begin with Barbara.
So I'm here. So I take the occasion to thank you and Santiago and Marco for involving me in this adventure. So I'm really far from your field. And so I'm happy for you Santiago, so I appreciated your presentation and the fact that you are, you are comfortable to present and to introduce your subject. The beginning of this adventure was not easy. You started with the COVID, and everything was delayed. And so now I prefer that is Marco to conclude this part, and so my best wishes for your future.
Thanks, Barbara.
So
okay, now it's your turn, Marco, to conclude.
You can.
Yeah. Okay. So I guess I can
Take it.
I can continue. Can they listen to me or can they hear me? Yeah, I think it should be okay, right?
Okay.
Yeah. Well, yeah, it's a weird moment being here for your project and for this adventure, as Barbara called it. We started long time ago. I remember when we had our first discussion with Eduardo. You were in Colombia, and there was this opportunity to work for an internship. And then you came here, you did a great work. It was really exciting as a moment, because it's a moment that I realized that federative learning was something that could happen in practice, thanks to you, actually, what you did with the first software, and then this work that we published at ISPI, and that allowed to take some, it was the initial seed of idea that I initially worked with Andre when I was still back in London for my postdoc. And then thanks to you, it concretized. And with that, actually, we started your PhD and much, much more, actually. So thanks to your work and your contribution, actually, there was something much, much bigger that started and developed, actually, to what it is now, which is a big component of the research activity of my activity and also of the team. So in this, I would like really to thank you, because without you, I think we will not be here with all what we have now in terms of positioning and production and scientific also insight that we got. So I think this is a very, very positive contribution side. And it was a complex project because we started many things, as you have shown. There are many things that I believe they still require more understanding. And so perhaps your project was useful to open some path that might be also like matter of study for other students, other projects. So this is also very nice. And then there is also what you did for Fed Biomed, which is how I always told you this is your creature somehow, because again, it's thanks to your initial contribution that then this project became something which is growing, is becoming quite important for the institute itself. So, and everything, imagine that everything started from like your internship, and at the time we were not completely aware of actually what was happening. And I would like to stress also that you were, at least to the best of my knowledge, what you did, so it was the very first application, like in the real world, with multiple institutes across the world of federated learning on medical images. And I think it's a pity because this is not something that at the time had the resonance, but I think this is well, quite remarkable actually. And I'm quite proud actually to present this also when I present what we do. So all of this to say that it has been really a pleasure and an adventure that I'm happy to have shared with you to get up to this point. And I thank you again for all what you did, also for all the social, like all your contribution to the team beyond the scientific aspect. You have been like a very, very active component socially. And so this was also very nice in terms of like daily life in the team. And I wish you all the best for the rest, for your career, your choices, and yeah, I think you truly deserve it. So thanks again.
Marco. So.
Okay, thanks, Marco. So now we have to deliberate. Do we stay in this Zoom or we have to move elsewhere?
I will move you to another room, I think. So I will create it right now.
Yeah, or you can stop the recording already.
Yeah. It's gonna not gonna do
Yeah,
it.
but I think it's true. And also the streaming.
Hmm. Wait. I know.
My
Breakout rooms. All right, you should be able. Yes. Okay. And do you have the sound and everything? You need to join to the breakout room. Cool.
So can you hear me?
No, no, sure.
Can we begin, Marco?
Yes, I think you can proceed.
Okay. So, Santiago, we had a long deliberation, and the jury really enjoyed your presentation. It was really, really clear. We enjoy your illustrations and your examples. And we also appreciate a lot the way you answer to the questions, the criticism, and your realism about the good and bads of what you've been proposing. Everybody was really impressed by the fact that you deal with a lot of data sets, which is not that usual in the field. It requires a lot of work. And of course, the fact that you've been involved deeply in the development of the software framework behind your algorithmic world, which is very time consuming, and I hope will be very successful. So for all these reasons, the jury has decided to give you the title of PhD of the University Côte d'Azur. Congratulations.
Thank you. Thank you.
Marco,
Muted, yeah.
There is a last formality that you should read a statement of scientific integrity now that you are a PhD. And so it should be this little paragraph here, which is mandatory by the university.
Okay, it does make sense, I guess. Having completed, in the presence of my peers, having completed my doctorate in automatic traitement du signal et des images, and having thus practiced in my quest for knowledge, the exercise of a demanding scientific research by cultivating intellectual rigor, ethical reflexivity, and respect for the principles of scientific integrity, I commit myself for what will depend on me in the continuation of my professional career, whatever the sector or the field of activity, to maintain an honest conduct in my relationship to knowledge, my methods, and my results. Thank you.
Very good.
Thanks. Maybe I don't need this. Thanks to the jury. I think this is the acknowledgement part. Yes. Yeah. Well, thank you, Marco. Really for directing this work. I know I can be hard sometimes, and you have been very patient with me in the toughest times, and this I really appreciate. And thank you for leading me here, because after all, you've been the director of this project. And thanks, of course, Andre, as well, for these 6 months. Also the guidance in London. It was a nice experience to meet the people at the Combined Lab. And also special thanks to the team. Most of the people are not here because they are gone. So thanks to them, and of course to my parents, to my family, to my girlfriend that also made this last moments that can be stressful sometimes easier. And yeah, I will give thanks then personally to each one of them. But thank you, James, Jonas, and everyone in the jury for making this project a variable. And Jean-François, of course, as well. And Barbara, thank you very much. Thanks.
Okay.
Oh, okay.
So,
Thank you.
Okay, we can say goodbye and leave you to the conference for those
yes.
who are in Canada, or
your
like
experience.
have a good rest of the day. And thanks a lot actually for your time and your help and the question. And thank you very much. I hope we can meet soon in person, the very next opportunity. So thank you. Thanks again.
bye-bye, everybody.
Thank you
Bye-bye.
very much.
Hey, congrats, Santiago.
Congratulations.
Well done, Santiago.
Well done. And congrats from everybody from London, and greetings from Neil. Yeah.